So in this video, we're going to start talking about linear approximation and differentials. This is a really important topic. One of the main things that we're interested in tangent lines is that they give us an approximation of a function by a line. Lines are really easy to calculate. They're really easy to use. So this is often a really good way to take a function that's complicated and simplify it. So let's see what we mean by this. So as I said, the tangent line of a function is very useful for approximating values. So suppose we're given a function y equals f of x, and we can evaluate the function at some point a. So this is super important. You need to be able to evaluate the function at a. If you don't know what that function is at a, you can't do a reasonable, you can find a tangent line there in terms of an equation, but it's not useful for approximations. So if we can evaluate it at a point a, and if we have some value b that's close to a, and we're interested in what f of b is, we can use the tangent line to approximate the value of f of b. So let's see an example of this to see what we're talking about. So suppose I'm interested in approximating the value of square root of 5. Well, to do this, I can let my function be f of x equals square root of x. And now I need a value, so if I'm looking to approximate f of 5, which is square root of 5, I need a value of a that's somewhat close to 5 where I can evaluate the function. So one such value would be if a was equal to 4, because I know f of 4 is square root of 4, which I know is equal to 2. So we choose that value, and then we can find the tangent line. So I know that the slope of this tangent line is the derivative of f at 4. So the derivative of f is 1/2 x to the minus 1/2. So if we plug in the 4 to that, I get 1/2 4 to the minus 1/2. So 1/2 times 1/2, which is 1/4. And if we evaluate the function at 4, we get 2. So if we use point slope formula for our tangent line, the tangent line is given by y minus 2 equals 1/4 x minus 4. If we go ahead and solve this for y, we just bring that 2 to the other side, and let's call this function L of x. We use L here to stand for linear. So this is the tangent line function that approximates f of x. And so we know that this tangent line should be somewhat close to f for x values near 4. So in particular, this means that square root of 5, which is exactly equal to f of 5, is approximately L of 5. And the nice thing about the tangent line approximation is I can actually evaluate that function. So I plug in 5 for x, and I get 2 plus 1/4, 5 minus 4. So this is just 2 plus 1/4, which is 2.25. So that tells me square root of 5 is approximately 2.25. And if you were to go ahead and plug this into your calculator, you'd get that square root of 5 is about 2.23. So our tangent line approximation is a pretty good approximation. It's off only by 2/100ths of the value that your calculator would give. And you can see this is very easy and quick to do. So let's see a picture of what's going on with this. So here is our graph. So the blue graph here, y equals square root of x, is our function f of x. And then we see the green line here is the tangent line at x equals 4. And if we go up here, we can see if we go to 5 here, it probably would have been helpful to zoom in a little bit. If we go up to the red dotted line, that's the value of where it's actually touching the function. So that's actually f of 5, which is square root of 5. And then you see the purple dotted line just above it. That's where L of 5 is. So we see they're very close together on the graph as well. So here we've zoomed in some. So notice with the scaling on the x and y axis, we've zoomed in quite a bit. And now you can see the difference here. The red dotted line here, that's the exact value of y equals f of 5, so square root of 5. And then the other value is, the purple value there is the value of L of 5, which was 2.25. So you can see as long as our B value we're looking at is fairly close to the A value, we get a good approximation just using the tangent line. So this is really nice. It's saying we can use, even though this function might be complicated, so square root of x isn't super complicated, we can use more complicated functions. We can approximate it pretty decently with a line. This is also often called the linearization of the function because you're taking the function and you're pretending it's a line for values of x near a. So just to summarize here, what we're doing, we have that the tangent line here at x equals a is given by y minus f of a is f prime of a times x minus a. We go ahead and solve that for y by bringing the f of a to the other side. And then we denote that function by L of x for the linearization of the function at x equals a. And then for values of x that are close to a, we have f of x is approximately L of x. So there's another way we can look at these by using what are called differentials. So sometimes we're not as interested in what the value of the function would be at b, but we're interested in what happens if I take a value of x that I know and I change the x a little bit. How does the value of the function change? This can be related back to the same thing with the tangent line approximation, but this can also be useful for if we're just interested in the change of f. So we define delta x, which is also denoted as dx, to be b minus a. So this is the change in x between the two values that we're in, the value we know and the value we're interested in. And we set delta y to be f of b minus f of a. So this is the exact change in y. Normally we can't calculate this because we know f of a, but we don't know f of b. So if we knew delta y and we knew f of a, we'd know exactly what f of b is. So what we're actually going to do is we're going to say, well, we're interested in this delta y, how the y changes if I change x. So I'll approximate this instead of being able to calculate it exactly. So notice, so if we set dy to be f prime of a dx, which is f prime of a b minus a, we can notice here that this f prime of a times b minus a, this is exactly the same thing as L of b minus f of a. And now we know how to evaluate L of b. So this is something we can actually calculate. And so now we're going to use the fact that delta y is approximately dy, and we can calculate dy, so that'll help us approximate delta y. So let's get a picture of this because it's quite a bit of words there. It might be a little bit complicated, but once we see a picture, it will help. So here's my function in blue, y equals f of x, and then I've calculated the tangent line here, which is L of x. Now, if I'm interested, say over here at 0 is my a, and then say over here at 0.5 is my b, well, the exact difference between the height here and the blue at 0.5 and at 0, that's delta y. So that's the difference between f of b and f of a. And now instead, I'm going to approximate that with d of y, which is the difference between f of a, which we can calculate, and L of b, which here. So you can see the red distance here, this is dy, the purple distance is delta y, and we're saying delta y is approximately dy. And you can see the smaller the gap between a and b, so if I took my b over here somewhere, the difference between these two would be very small. I've just illustrated it with a little bit further away so you can see the difference between the delta y and the dy a little bit better. So let's see a couple of examples of how we can use differentials. So first, let's just use it to approximate e of 0.5. So here we'll take a to be 0 because that's something I can evaluate f at. I know f of 0 is just going to be 1. And we'll take b to be that 0.5 that we're interested in. Now, the dy here is f prime of 0 times dx, which is e of 0 times 0.5 minus 0. So this is just 0.5. So delta y is approximately dy, which is 0.5. So that means e of 0.5 minus e of 0 is approximately 0.5. Or e of 0.5, bringing the e to the 0 to the other side, is e of 0 plus 0.5, which is 1.5. So this is really just a tangent line approximation in other language. So in this case, this isn't really anything new. from what we've already done. We'll see the next example does give us something that we could get with tangent line approximation, but is easier with differentials. And here, if we plug this into the calculator, you get 1.65. Okay, so let's do an example now where differentials are a little bit more useful than tangent line approximation. We could use tangent line approximation, but differentials makes this a little bit easier in this case. So suppose we have a hemispherical dome of diameter 50 meters, and we want to apply a coat of paint to it. So a hemispherical dome means just basically the top part of a sphere. We want the coat of paint to be 0.05 centimeters thick. So we're going to use differentials to estimate the amount of paint that's needed. So the volume of a hemispherical dome of radius r is given by V of r, which is 2/3 pi r cubed. Notice the volume of a sphere would be 4/3 pi r cubed, so we've taken half of that to get the volume of the hemisphere. And now what we want to think is, well, when we apply a coat of paint 0.05 centimeters thick, we're changing the volume by a little bit. So we can say the dr, we've changed r by, we have to change the 0.05 centimeters to meters, and then it's 0.0005 meters. So then my dv is the derivative of vr, so 2 pi r squared dr. So our estimate here is that we should have 2 pi, and then the radius here is 25, since the diameter is 50. So we have 2 pi times 25 squared times the dr. So this is about 1.96 meters cubed. And so that's how much we estimate the paint to be. So we'll see some other examples in class of how differentials can be used as well.